All right, so here's what brings up. Here's our initial state. Here's an insulated box with a boat, some mass of ice at 0 degrees Celsius, and some amount of vapor at 100 degrees Celsius. Now the area at the bottom is 25 centimeters squared. Its height is 10 centimeters, and the radius of the spherical surface is 1 meter. We're also told that this is a reflective index, the same as water, so that's going to be 1.33, and this is just air, so that's 1. We know the final state, you see it's all water, no ice, and all the water is 100 degrees Celsius, which means it's reached equilibrium, which means thermal equilibrium. There's less vapor, and the boat creates an image seen by the eye that's 20 meters away, centimeters away. So what we're looking for is mass of ice. Let's figure it out. So find the mass of ice. The best thing we could do is find however much water is here, and then figure out the ratio of ice to vapor, right? So let's first find out how much water is there, and call that mass of water. So we can use the relationship that mass over density is equal to area times height, right? Well, we know density is just 1 gram per centimeter cubed. Area is 25 centimeters squared. So let's just find height. I'm going to save that over here at mass equals area, height, density. So let's first use the equation for spherical surfaces. That's going to be n1 over s plus n2 over s prime is equal to n2 minus n1 over r. Now, we're looking to isolate s, right? So first let's flip it. No, we're going to first put this over here. So that's n1 over s is equal to n2 minus n1 over r minus n2 over s prime. Now we're going to invert it, so it's s over n1 is equal to 1 over that whole mess, that's going to be n2 minus n1 over r minus n2 over s prime. Just for the sake of not having to rewrite all that, we can just multiply both sides by n1 to isolate s fully. Plugging things in, we get n2 is 1 minus n1, 1.33 over r, which are told us 1 meter. But if we're going to work in centimeters, that's the same as 100 centimeters minus n2, which is 1 over s prime, which we'll see is 20 centimeters under n1, which is a1. S is equal to negative 24.95. Now, what does that mean? Well, it means because it's negative, it's going to be on the other side of the outgoing side. So it's not going to be coming out this way. It's actually going to be coming out this way. It's going to be coming out 25 meters this way, centimeters this way. So we know top of the water is 25 centimeters. So logically, we know this is at 25 centimeters. And then we're told here that this here is 10 centimeters away. Of course, 25 minus 10 means this chunk here is 15 centimeters. Let's save that. That's going to be height equals 15 centimeters. So knowing that, we now know what area is, we know what height is, and we know density. Let's put it all together. That means mass is equal to area, that's gonna be 25 centimeters squared, keep track of our units, times height, 15 centimeters, that makes it centimeters cubed, times density, which is just 1 gram per centimeter cubed. What we're left is 375 grams. Let's save that. Mass of water is 375 grams. Change colors here. So, what can we do with that? Well, again, let's find a ratio between the ice and the vapor. Consider the fact that this is in thermal equilibrium, which means in the middle, there had to be some point where the ice melted at 0 degrees, and some of the vapor cooled down into water at 100 degrees, right? And then the water could heat up to 100 degrees Celsius, but even then, the vapor would have to condense. So let's figure out what's going on there. Let's first find out how much energy it took to melt the ice down to water. We do that using the equation for heat capacity and fusion. So that's going to be Q equals LF sigma M. So we're going to use LF, which is 334 kilojoules per kilogram. And then in place of mass, we're just going to use M ice, because that's what we're looking for. So now we know energy to go from water to ice. So it's 334 kilojoules per kilogram times mass of ice. Alright, so now let's figure out ratio for the amount of vapor in this step using the vaporization. It's going to be Q, which we know would be 334 kilojoules per kilogram times M ice is equal to vaporization, which for water is 2256 kilojoules per kilogram times mass of vapor. Now let's just divide over this way. What we're left with is units that cancel and number that says mass of ice times 148, or 0.148, excuse me, mass from step 1 to the middle step. So let's save that over here. Do the same, but from that middle step to equilibrium. Because we're going to equilibrium, there is a temperature change, so instead of using that equation, we can actually just use Q equals MCAT. It's not MCAT, MC delta T, but you know. All right, let's do it. So, energy of water, 0 degree water to 100 degree water is equal to mass, which we calculated as, we're not calculating, we just know it's just some value M, the heat capacity of water, molar heat capacity of water, or no, the specific heat capacity of water is 4190 joules per kilogram Kelvin. And then delta T would be 100 minus 0, so that's just 100, we're gonna just say Kelvin for the sake of units, because it's gonna cancel anyways. So what we're left with here is the energy from 0 to 100 is equal to M times canceled kelvins. No, it's just $41.90 with 2 more zeros, joules per kilogram. Now, let's do the same thing for vaporization. That's going to be Q would just be 41.9000 joules per kilo times our mass M is equal to F of V, or V of, wait, what am I saying? I'm saying L of V, excuse me, and that for water is 2256. And that's going to be kilojoules per kilogram. And let's convert that into joules. So that's 1,000 joules per 1 kilojoule. Now, kilojoule, joule, kilogram, times the mass of middle to final. And what we're left with is sigma M from middle to final is equal to 41.9000 over 2256,000 times our mass of ice, and that results in 0.1857. Right? Hold on. $419,000 divided by 2256,000 0.1857. Hold on. That does something wrong. Let's redo this, and let's see if we can diagnose where we went wrong. So we'll go with a different color, just for the sake of visual reset. All right, so let's restart it. We're going to go from that first stage, the middle stage, where the water is still at 0 degrees, and the water from the vapor is at 100 degrees. So to go from ice to water, we would use what's it called? We would use the equation for fusion. So that's the energy to go from the initial step to the middle step is equal to fusion, heat of fusion, which is 334 kilojoules per Kelvin, or no, per kilogram, excuse me, times our mass of ice. Now we can take that and we can calculate how much vapor has been produced by using that as a Q value. So we would get 334 kilojoules per kilogram times the mass of ice is equal to the heat of vaporization, which is 2256. And that's in kilojoules per kilogram. Times mass of vapor from initial to the middle. And what we get is that sigma value is equal to here we go. Okay, I knew something was off. We're gonna get 0. Did I just write it wrong? Are you serious? 0.148. These cancel, and we're just gonna get 0.148 times the mass of ice. So let's save that. The mass of vapor from the initial middle step equal to 0.148 times whatever mass the ice is. Let's do the same with the middle step to the equilibrium. Well, we're not going to use the same equation because we actually have a temperature change. So we're going to use Q equals mc delta T, which means energy equals our input, or I guess our standard M. Specific heat capacity of water is 4190 joules per kilogram Kelvin. And our temperature difference is 100 minus 0, which is just 100. And because converting from Celsius to Kelvin is 1 to 1, we're just going to put Kelvin there to cancel our units. What we're left with is energy to go from the middle to the final stage would be 4190, 2 more zeros, joules per kilogram times the mass of ice. So the same to get the vaporization. We're going to do Q vapor, or that is our Q actually. So our Q is 419123 zeros joules per kilogram times the mass of ice equal to vaporization, which is 2256 kilojoules per kilogram times the mass of vapor from middle to final. What we get is that mass is 419000 divided by 2256. Oh, wait, I need to multiply 2256 by 1,000 to convert from kilojoules to joules. What we're left with is 0.18. We call that 6. Yeah, 0.186. Kilojoules, joules, kilograms. So that's just 0.186 times whatever mass of ice we have. Now, we know how much of our vapor, or how much of the water, comes from vapor. Sum these two, just get mass vapor is equal to 0.23234 ice. So we get a value of mass of vapor is equal to 0.334, that of ice. And then, because it's our ratio, that's just considering the vapor. It's not considering the ice yet. Just add 0.334 times the mass of ice plus mass of ice equal to mass of water, 375 grams. That becomes 375 grams equal to 1.334 times the mass of ice, which means the mass of ice is equal to 281.11 grams, and we are going to get our sig figs down and just call that mass of ice is equal to 280 grams.